Well, it's going to be somewhat incomplete, but I mean, at least, yeah, you'll get the pictures anyway. So, in this case, Rolle's theorem, it's going to guarantee to us that between A and B, we have points for which the slope of the tangent line equals to 0. But in this simplest case, we have infinitely many points because this is a horizontal line and its derivative is going to be 0 everywhere, right? Let's look at something more interesting like the second graph. All right. So again, this is A, this is B, this value is going to be f of A, and this value will be f of B. All right. So, so when we go from A to B, and we have the situations in which both values of y are exactly the same, because if you look at the height of the functions at both values A and B, it's the same value. So this is actually to satisfy this condition, the fact that f of A equals to f of B. Well, this implies that for sure the graph will either attain a maximum, that is a point, a value C, whatever that is, and again, it doesn't have to be in the middle, but could be in the middle, a value of C for which the derivative f of C equals to 0. Again, recall that the derivative means slope. Slope of what anyway? The slope of the tangent line at this given point. And if we do that, that tangent line isn't that horizontal, which has a slope equal to 0. Another case. Let's consider the case, well, I'm going to take, well, this one is going to be a little bit tricky, so here and here. So A and B, all right? So in this case, well, this is f of A, f of B, all right? So Rolle's theorem guarantees that there is at least one number C for which the derivative evaluated at that value equals to 0. Well, in this case, for this function, notice in the interval A to B, actually we have two values, f prime of C and another, let's call this D, f of D, or f prime of D rather, for which the slopes at those points are 0. All right? And again, that's related to the fact that we can, so Rolle's theorem essentially is telling us that whenever the function is continuous in the closed interval and differentiable in the open interval, and lastly, it satisfies that f of A is equal to f of B, for sure there has to be at least one critical number. Once again, the definition of critical number, a value C for which the derivative equals 0, or for which the slope of the tangent line at that given point will be equal to 0, all right? So, and you can think of this as a physics application, you know, for example, when you throw up a rocket, for example, or a rock, and so you throw it, and it's going to do this, all right? So let's call this T equals to A, and let's call this T equals to B. So when you throw up a ball, you know, as a football or a baseball, whatever, and if you do the projectile motion way, well, there will be two different times for which this ball will be at the same height. That is the f of A equals to f of B condition of Rolle's theorem. All right? So let me put some, make him happy. All right? All right. So that's pretty much what Rolle's theorem is about, to guarantee a critical value. All right. So let's look at one example to see this in action. So let's consider the function f of x equals to x squared minus 5x plus 4 on the closed interval -1 to 6, and then show that Rolle's theorem can be applied to f on this interval. Then find the value or the values of z guaranteed by Rolle's theorem. All right. And then let's draw a diagram to illustrate the result. So in this case, this is what we're going to do. We're going to look at the graph of the function. So number one, let's determine the first condition. Is it continuous on the interval -1 to 6? Yes or no? I mean, it's a polynomial, so if it's continuous everywhere, sure, it's continuous at least on the interval -1 to 6. Okay. Number two, or letter B rather, it's a differentiable. Yes. But we need to be careful. The fact that the function is differentiable doesn't necessarily mean, I mean, it's continuous doesn't mean differentiable, but the reverse is true. Differentiable means continuous, because a function can be continuous, but what if I have a function with a cusp? At the cusp is not differentiable. All right, so differentiable on -1, 6. That has to be open interval. I will explain why in a minute. All right, so yes, it's differentiable in that interval because this is a polynomial again, and between -1 and 6 we don't have any jump discontinuities, any vertical asymptotes, any what else, holes, you know. Letter C is f of a equals to f of b. In other words, is f of -1 equal to f of 6? Okay, let's find out. Let's do the calculation. F of -1. So that's -1 squared minus 5 times -1 plus 4, and f of 6, that's 6 squared minus 5 times 6 plus 4. So that's a -1 squared, which is 1. Okay, careful. -5 times -1, that's +5. 5 plus 1, that's 6 plus 4, 10. All right. 6 squared, which is 36. 36 minus 5 times 6, which is 30. 36 minus 30, isn't that 6? And then plus 4, it's also 10. Well, so in this case, this is true. So in this case, this function satisfies the conditions for Rolle's theorem on the given interval. So this Rolle's theorem will guarantee that we are going to have at least one critical number between -1 and +6, and that's because, well, since we have the same height, f of a, f of b represents the same height. Either the graph is going to go increasing and then decreasing, which guarantees a maximum given by the critical point, or decreases and then increases, which in this case we get a minimum given by this critical value, or just goes in horizontal line, having essentially infinitely many points for which we have a slope equal to 0. All right, let's have a look at how do we go about that. So in this case, well, coming back to Rolle's theorem, so we need to do this. Find the derivative, evaluate it at c, and then set it equal to 0 to find that value of c. So f of x equals x squared minus 5, x plus 4. Let's take the derivative. That's 2x minus 5. But the derivative, we need to evaluate it at c to find that value of c, which is the critical value. 2x minus 5. And then this 2x minus 5, set it equal to 0, and solve this equation for c. That is 2x equals to 5. and divide both sides by 2. That's x equals to 5 over 2. All right, and well, 5 over 2 is actually equal to 2.5. So when we look at the graph to verify our result, make sense out of it. All right, so let me go to the graphing calculator. Okay, so the graph of one, oh come on, I have to continuously move to function mode, clear, and that's x squared. Is that a plus or minus? Minus 5x plus 4. And graph. So what do we have between -1 and 6? Do you see this critical number in between? Does that value correspond to 2.5? All right. So that's Rolle's theorem in action, right? Well, number one, algebraically and analytically and graphically. So this is the information this theorem is telling us. All right. This the main topic for this section, which is really the mean value theorem. Yes.
Can you go back up a little bit?
Sure.
So basically, if any of the conditions, like being at least one is not met, then we can.
No, it doesn't satisfy. For example, maybe the function is not continuous on the given interval. Well, this is a polynomial, so there's no issues at all. So and therefore it's differentiable. No gaps, no holes, no sharp corners, and well, typically the one that fails the most is f of a not being equal to f of b. All right.
And when it means draw a diagram to illustrate, where's your diagram?
Oh, it was the graph I showed on the graphing calculator. Yeah. So the mean value theorem. The mean value theorem is an extension of Rolle's theorem. However, Rolle's theorem tells us that there exists a value c between 2 points for which the slope equals 0. In other words, that word is a critical number, a critical value. However, the mean value theorem extends to find points where, number one, the slope of the tangent equals the slope of the secant. In other words, typically I call this where algebra meets calculus, because here we're looking the values for which the slope of the tangent is equal, which we get using calculus, equals the slope of the secant, which we get using algebra. All right, a picture for this. So suppose we choose these 2 points. Let me call this point and that point. All right. So this is A. This is B. And I'm going to draw a secant line between these 2 points. All right. So recall, secant lines involve using 2 points. So somewhere in between A and B, there has to be a value of C for which we can draw a tangent line having the exact steepness, the exact slope, as the line that we get when we use 2 points, that is a secant line. Well, could it be at this point? Well, no, in this case the slopes are not the same. So we need to find that point. So think of dragging this line right here. So if I drag it, I will find out that over here, roughly, we have no. Let me see if I can. So control. No, I cannot copy. Okay. No. Let me see if I can drag it instead. Move it up. So that's now a tangent line. All right, and no more like a secant line. So in this case, this is M of the secant line, and this is N of the tangent line. All right, so we're going to look for that value of C for which the 2 slopes are the same. And you might ask yourself, well, what do we care about that? Well, this is a very powerful theorem that it's used to prove a lot or to apply to many other theorems and situations later in other topics. So that's one example, right? Taking these two points right here. And another possibility, okay, let me erase all this. What if I take this point, for example, and that point? So notice in this case I'm using a totally different interval here, not the same interval. So when I draw the secant line, all right, there's more than one possibility in this case for which the slope of this secant line is exactly the same as the slope of the tangent line, and in this case, well, it looks like over here we have one case. All right, does that tangent line seem to have the same slope as this secant line? Yes. There's another possibility though. What about this one? Does that line contain or has the same steepness as the secant line? So that's let's call this, well, this is A, this is B. Let's call this C1 and let's call this C2, because there's more than one possibility. In some cases we may run into this situation, more than one possibility. And again, this is M of the secant line, and in these two other cases it's the M of the tangent line, and that's because, well, that's just touching one point as opposed to crossing through 2 points. So that's the picture. So that's what the intermediate value theorem. So it's an intermediate value, a value between A and B, not necessarily in the middle, but it could be in the middle, for which the slope of the secant is the same slope as that of the tangent. And of course we need to have a look at a couple of conditions. In this case, only two conditions. The function is continuous and differentiable in the interval. We don't have to check the f of b minus f of a have to be equal to each other, because check this out. What's f of a here? Is this f of a the same as this f of b? It's not anymore. It's different y values. We have to have the same y values only for Rolle's theorem, not for the intermediate value theorem. Let's do a couple of examples of the mean value theorem. All right. So determine whether the function f of x equals to x cubed minus 3x plus 1 satisfies the conditions of the mean value theorem on the interval 0 to 2. If so, find the points guaranteed to, or the points guaranteed to exist by this theorem. That is, in the interval 0 to 2, all the values or the single value that has the same slope as the tangent. So number one, we need to check a couple of conditions. Number one, or letter A, is it continuous on 0 to 2? Yes or no? It's a polynomial, right? So why not? What about B, differentiable? On the open interval? Yes or no? Yes. So we can go ahead and use that mean value theorem. So number one, let's combine the value of the slope. Let's get the value of the slope in this case. Okay, so no, the slope of the secant and the slope of the secant, it's simply y2 minus y1 over x2 minus x1. All right, so, and y2 is going to be the function evaluated at the upper bound, and y1 is going to be the function evaluated at the lower bound of the closed interval. So f of 0, that's going to be 2 times 0 cubed minus 3 times 0 plus 1, that equals to 1. All right? F of 2, that's 2 times 2 cubed minus 3 times 2 plus 1 equals 2. Okay, so that's 2 cubed, which is 8. 8 times 2 is 16. 16 minus 6, isn't that a 10? Plus 1? Isn't that an 11? So let's see. So we're going to look at the slope m. That's y2 minus y1, or equals x2 minus x1, which in our context, f of 2 minus f of 1 over 2 minus 1. All right? So f prime of c equals f of 2 minus f of 0, or f of 1, oh, hold on, it's f of 0, not 1. So the result was 1, all right, 2, 0. And f of 0 over 2 minus 0. So this result, so 11 minus 1 over 2, so that's 10 over 2, which equals to 5. So that's going to be this result, 5. What's f prime of c? So number 1, take the derivative of the function, so f prime of x, the derivative of the original function, okay, let me zoom it out, the derivative of 2x cubed, that's 6x squared minus 3, and evaluate at c, and that's going to be the left hand side of the equation. So 6c squared minus 3.
6 minus 5 squared.
So just solve for c in this case. So add 3 to both sides. So that's 6c squared equals to 8. Divide both sides by 6. That's c squared equals 8 over 6. And that's 4/3. And take the square root on both sides. So c squared equals plus or minus the square root of 4 over 3, which is plus or minus 2 over the square root of 3. But be careful here, because we will have essentially c1 equals negative 2 root of 3, and c2 equals positive 2 root of 3. However, yes, we obtained two different results. This doesn't mean the two results are correct. We need, number 1, to check our interval that we're working on, all right, which is the interval 0 to 2. Is the first solution within that interval, contained in that interval? No, so we need to ditch that solution. Is 2 root of 3 between 0 and 2? For sure. So this is the value for which the slope of the secant for these two, within these 2 points, it's exactly the same as the slope of the tangent at this point to 2 over root of 3. All right, so that's the mean value theorem. So this is the mean value right here. All right, let's look at another example. Find the value or values of c guaranteed by the mean value theorem for the function f of x equals the square root of 2 minus x on the interval -7 to 2. And well, let's draw a diagram to illustrate this result. All right, so how about we start drawing the graph of the function, so we get an idea of what the function is going to look like.
So we can do the steps first, right? To see if it works out.
Let's do that first. That's true. So, number 1, well, since this function it's no longer a polynomial, it would be a good idea to find the domain of the function. So, find the domain. And well, to find the domain of a radical function, we set the radicand 2 minus x greater than or equal to 0, negative x greater than or equal -2, and well, when we get x by itself, to get x by itself, we need to divide both sides by -1. But what happens on an inequality when we divide by a -1? We need to reverse the direction of the inequality, right? So that means the domain of the function is all the settable numbers less than or equal to 2. So that is the largest input we can plug into this function. It's x equals to 2, and in fact that's the upper bound of the interval. Well, so -7, it's also part of the domain, so in this case it's continuous, right? So it's based, the graph of this function, okay, let me draw it. So that's second square root 2 minus x. It's a radical function shifted 2 units to the right and then reflected vertically, right? So so like this. So letter A, continuous. Yes. Letter B, differentiable. It's also differentiable, all right? Between -7 and 2, there doesn't seem to be any asymptotes, any jump discontinuities, any holes, or anything like, or any cusps, you know? And well, so continuous on the closed interval. I think this is a good moment to explain why it should be differentiable, not in the open interval, but in the closed interval. I mean in the open interval. And that's because, well, what happens if we try to find the derivative at the edge of the function? Okay, so the derivative at this point, it's only one tangent line. Do we agree with this? It's only one possibility. The derivative at this point is only one possible tangent line, so that's fine. But what about at the edge right here? Did you notice something weird here? So at the edge, we have this possibility, infinitely many possibilities. So for this reason, we need to check for differentiability in the open interval, that is from -7 to 2, but excluding the endpoints, right? Only all the points in before the upper bound and after the lower bound. All right. So so let's find the derivative, or no, let's do f of -7 and let's do f of 2. So that's going to be the square root of -7 plus, or what is that? Oh no, that's 2 minus -7. That's the square root of 9, which is 3. And that's the square root of 2 minus 2, which is square root of 0, which is 0. So the slope of the secant line, which will be this one right here. So that'll be that should be a negative slope. Let's verify that it's true. So that's y2 minus y1 again over x2 minus x1. So in the context of our function, this is f of 2 minus f of -7 divided by 2 minus -7. Careful when subtracting the values. Careful with the negative sign. So that's f of 2, which is, oh actually, no, that's fine. 0 minus 3 over 2 plus 7, which is 9, which is -3 over 9, which is -1/3. And indeed, this checks with our graph, right? We have a secant line with a negative slope. Now, let's find that value in between -7 and 2, for which the tangent line will contain the same slope. So we're gonna do take the derivative f prime of x. So that's gonna be number 1. Let's rewrite the function f of x equals 2 minus x to the 1/2. and do a mini chain rule. 1/2 2 minus x to the negative 1/2 times the derivative of 2 minus x. Be careful, what's the derivative of that? Negative 1, right? So this means negative 1 over 2 times the square root of 2 minus x, f prime. And well, let's define this as f prime of c. Alright, so we're going to set this quantity, the slope of the tangent, equal the slope of the secant, to find that value of c that will give us that will contain a tangent line with the same slope. Alright, so this is negative 1 over 2 root of 2 minus c equals to negative 1/3. Okay, to solve this equation, let's cross multiply. Also, we can change those minus into pluses. So that's going to be 3 equals to 2 square root of 2 minus c. And how about we square both sides? Square, squared, and that to get rid of the radical, that's going to give us a 9 equals to 4 times 2 minus c. And well, so this is 4 times 2, that's 9 equals to 8 minus 4c. And in this case, well, 9 minus 8, that's negative 4c equals to 1, and c equals to negative 1/4. Alright, so that means that c equals negative 1/4, which is roughly here. That's the point where we will have a tangent line containing the same slope. And then, judging by the pictures, does that check our hypothesis, our work with our definitions? Are you guys following me here?
Yes.
This is making sense? Let's do one more example. One more example and we call it a day. Alright. Determine whether the function f of x equals 1 over x satisfies the conditions of the mean value theorem on the interval negative 4 to 4. And if so, find the point or the points guaranteed to exist by the mean value theorem. So number 1. Or rather, letter A, is the function continuous?
Yes.
On negative 4 to 4?
Yes.
Yes? No. What's the domain of f of x equals to 1 over x? Isn't this x cannot be equal to 0? Or graphically, we have a vertical asymptote between negative 4 and 4, alright? So, no. This means the mean value theorem does not apply. What about, how about in the interval 1 to 4 though? Would it satisfy the conditions? And that's because between 1, 2, 3, 4, well, oh yes, it's continuous in that interval, but unfortunately not in the interval negative 4 to 4. So again, when it comes to polynomials, I mean, that goes pretty straightforward, because for polynomials we don't have any restrictions with asymptote, faults, comes to discontinuities, cost when it comes to differentiation. However, we're different functions like rationals, like logarithms, like radical functions like the one we did. We need to find the domain first, and then based on that determine whether that interval that we want to study about the function is indeed in the domain. Otherwise, we simply say does not apply. We're done, like in this case. And this is all I have for today. So if you have any further questions,